All right, so what do we have? What ideas do we have about ionospheres on Dana 1? Anyone here? What are your thoughts? Does Dana 1 have an ionosphere? Huh? Okay. From a B star. Okay. Yeah, something like that. Right, this is 4 times hotter than the sun, maybe 3. So that's going to move it from 2 electron volts up to about 6 electron volts. So what does that tell you?
I wasn't listening, I'm sorry.
I'm trying to see if anyone has any ideas, any thoughts on the ionosphere for Dana 1. What? There are a lot of photons. They're hotter than the sun's. Well, are they hotter than the sun's photons? Remember, I'm a physics professor, so a lot of the information I provide in the problem may actually not be relevant. Students love when you do that. Did any of that story have anything to do with the intensity of the radiation? I mean, what was the key thing? What was the is that how, did I talk at all about that? I talked about the solar wind on Tuesday. Of the three questions, like the Earth has the sun has a magnetic field because it has a dynamo. It has a corona, and it has an ionosphere. Why? Not because of its brightness, not because it's a 6,000 Kelvin photosphere. X-rays. Would a B star have any X-rays? Right. So forget about the core. The core doesn't do anything. What about the part that's going to be out at the surface? Remember, I showed you a Hertzsprung-Russell diagram, and I showed you where the magnetic activity was. Of course, it's an astronomy plot, so the hottest stars were all over on the left. The B stars were probably not even on that plot. What do we need for a dynamo? What is the main part of the solar dynamo that Mark Misch talked about at great length? They don't have a convection zone. Convection zone generates the magnetic field. The magnetic field generates the corona. The corona generates the X-rays. The X-rays generate the ionosphere. See, B star is hot, but doesn't have any X-rays, or EUV for that matter. It's got nice, ultraviolet type photons that might have a good ozone layer, but no ionosphere. M dwarf, much cooler, much fainter. But what about the X-rays? Like gangbusters. Those things are X-ray superstars because they're all convective. Yeah. So it's you got to think about the X-ray part, and for that you have to think about the convection zone. All right, but let's talk about the solar wind. So we do have a solar wind, and it's coming up to, let's just think about some non-magnetic body like Mars or Venus. So a solar wind is coming up to this thing. Now first you'd say Mars is like a rock. So what does my plasma care about a rock? It doesn't really. But we've just talked through the fact that, well, it's got an atmosphere, and that atmosphere is being ionized by the X-ray radiation from the sun. So now it's got it's a rock surrounded by a big conducting layer, right? Like a rock in aluminum foil. Okay, the magnetic field at any rate is going to care a lot. It cannot penetrate that, so it is not going to go into the rock, and it has to go around. All right? Our flow is supersonic. We talked about that. Once you get out past a couple solar radii, you're going supersonic. You get to Mars, you're still going supersonic. We talked about this quite a bit during the lab yesterday. So I basically have this obstacle in my supersonic flow, and what that generates is a shock. Okay, we have a shock that basically slows the flow down, and then the flow is subsonic behind the shock, and it goes around the planet. What it actually goes around isn't the planet. It goes around the ionosphere. It's the only part it cares about. But the ionosphere happens to be surrounding the planet, so it goes around the whole planet. Okay? This is a structure of the bow shock and sort of the, I guess it would be called the magnetopause, but there's no magnetosphere here. And I'll just show you a very, it's not super simple, but if I said, well, it's a subsonic flow behind the bow shock, so actually if it were really, really, really subsonic, it would be an incompressible flow. Right? That's really what incompressible flow is. It's subsonic flow. Don't let anyone tell you, oh, water's incompressible and therefore flow in water is incompressible. Air is compressible. Air is not compressible, right? If I take my hand here, I cannot compress air. Why not? Because I can't move my hand faster than the speed of sound, right? If I could move my hand at 1,400 miles per hour, I would have a nice high-density region in front of my hand. I'd have a shock. But once I go through the shock, I'm subsonic, so I'm incompressible. Here's a nice, well, it's sort of nice, analytic version of the flow around a spherical object that's incompressible. So if it's incompressible, I can write it using this stream function. This is a nice stream function from Lighthill. I do a little bit of algebra. This is on the web, so I'll let you do this. It's kind of cool. I can find that if I am hypersonic, so this Mach number is effectively infinity, it doesn't really matter at that point, and then I go to subsonic, I have a bow shock here that is 1.18 times the radius of the spherical obstacle. That's known as the standoff distance. And lo and behold, if you use sophisticated numerical calculation, you get close to the nose here, a very similar type of flow. Okay, and downstream it looks somewhat different because, of course, I wasn't using the right form for that. One of the things that happens when you go through that shock is your temperature goes way, way up, and actually it goes up slightly higher beyond that, but you raise the temperature inside this magnetosheath. So I don't want to go through the math. I put it all on the web, but we now see that when we have flow coming into Mars, you have this bow shock where the supersonic wind gets a surprise, hears that there's a planet, an ionosphere in front of it, and it goes around the ionosphere. Okay? So that's sort of the story of how the solar wind encounters these unmagnetized planets. So similar story for Venus. As I say, one of the reasons I want to bring all this up is, yeah, this is all stuff that's part of heliospheric physics and part of the textbooks. The story for the Earth is quite a bit different because the solar wind does not see the ionosphere. The ionosphere is way down in there, right where it should be, out of the way. We don't have to worry about it, right, Jan? What the solar wind is going to see is this magnetic field that was generated by our dynamo in the center of in the liquid core of our planet. And that extends out around the Earth. And that's a magnetic field and a plasma in the magnetic field. And so the solar wind sees that and has to go around that. Okay, so the magnetosphere is formed from that. And it is, the magnetosphere does the deflection. But unlike an ionosphere that's built in a thin atmosphere around a planet, this is more of a squishy obstacle. Right? Now I do have to start worrying about some of the things people were talking about here, ram pressures of the solar wind. The harder the solar wind pushes against this squishy object, the more it squishes the object. So the size of the magnetosphere is not going to be that simple to calculate. But here we have another nice analytic formulation. This, I think, this is also due to Chapman. Some of the nice analytic stuff here was due to it. Imagine you had the Earth's magnetic field was a dipole. I talked at length about how it's not. We did see that when you get farther away from the Earth, that's sort of what it's like. And imagine it had some region that it was controlling to deflect the solar wind, and that region was perfectly spherical. Well, in case you don't remember, the spherical harmonic for L equals 1 is cosine of theta. So there's all of the YLMs we're going to involve ourselves with, but I'm using the same trick. B is minus the gradient of a scalar. I say curl B is equal to 0 there. We've seen this trick about 4 times so far. So I just have cosine of theta, and it falls off as 1 over r to the L plus 2, L plus 1. Chi does. And B falls as 1 over L plus 2. So there's the 1 over r squared term. Why do I have an r to the 1th term? R to the L term. This is sort of similar to something we did with the potential field source surface model. Remember, I had the magnetic field decaying with distance as I got away from the sun, but I also had terms that grew with distance as I got away from the sun. Why did I have those? Graduate physics class consideration. Teach Jackson, and like 2/3 of the class, 2/3 of the time I'm in Jackson, we're always worried about boundary conditions. I had to have those other terms to match the boundary, which for a spherical, a potential field source surface model, what was the boundary condition on chi when I got to the source surface, 2.5 solar radii? What had to happen to chi? Well, the field was perfectly radial, so chi went to 0. Yeah. Right, so actually I had a minus sign there. Here, what has to go to 0? Chi? Chi isn't going to 0, I'll tell you that. What? Grad chi, or d chi dr. Br. Instead of b theta and b phi vanishing, I need br to vanish, because it's inside of its little bubble. Yeah, so the field lines can go any way they want, they just can't cross it. So this is a Neumann condition before we had a Dirichlet condition. This is classic Jackson problems. Solve the problem. Problem 11, solve with Neumann conditions. Dirichlet conditions. Problem 12, solve it with Neumann conditions. Here's the Neumann condition version. Okay, so that's sort of an image of, that's sort of the image of the magnetic field close to the sun. So there's the dipole term, and this is due to the image, which is basically confining it. So when you have that, you can take the derivative, you can find what B is right at the nose. That's the strength of the magnetic field that the solar wind sees. And if the only thing it has to balance against is ram pressure, then you find out that the magnetopause has to be at a distance that's given by a balance between these two. And it basically has to do with the magnetic field strength that the Earth has divided by the ram pressure of the solar wind to the 1/6 power. I'll let you go through all this math, and then some factors. So as the solar wind has higher density and lower flow, has higher density, you're going to get a magnetosphere that is pushed in. Okay? We would often use this kind of thing in our graduate oral exams. Have the student work out how far away the magnetopause is. That's like 10 Earth radii, 10 or 12 Earth radii. There it is, 12 Earth radii. You plug it all in. That's with this solar wind density, 400 kilometers per second. I want to just get a few more numbers in my mind, because this is telling me how big the Earth's magnetosphere is. Some people might even know this. In terms of Earth radii, our GOES satellites, my TV dish network satellite, where are they? How far away? 6.6, okay. Very good, you know it. The way I work it out is a low Earth orbit satellite is orbiting in 90 minutes, 1.5 days, 1.5 hours. GSO, 24 hours. And since you always have to remember Kepler's law, the distance is that ratio, 24 divided by 1.5 to the 2/3 power, 6.5. Simple answer. So those satellites, in the magnetosphere or out of the magnetosphere? They're less than 12. So they're safely nestled inside the Earth's magnetosphere. Yes, okay. So we saw that this distance depends on the ram pressure of the solar wind. So if that goes way up, I could have my magnetosphere shrink in. It's squishy. I could leave my dish network satellite hanging out there in the wind, so to speak. Yeah, so very important point. The moon. Is it inside the magnetosphere or outside the magnetosphere? There, by the way, is the period of the moon, 28 days, 24 hours, 672 hours. Kepler's law. Kepler's third law. Outside. What's the radius of the orbit? Oh. John, you're not allowed to answer this. You're not allowed to answer this. Can't take 2/3 powers in your head? Okay. It's 60 Earth radii. So it's outside. So the Earth is outside the magnetosphere. Outside the magnetopause. I'm going to get to that next part. So if we have fast solar wind, and if the density stayed the same, which is not really true, we can pull, just for fast solar winds, we can pull the magnetopause into sort of 9-ish. But Jan's point is, for a big disturbance, a CME or something with high density, maybe even high velocity, we can get this even smaller, okay, and we'll be inside. Okay, I don't know why I have the extra there. This just sort of shows I've been talking simple things, and I want to just cover a couple of other things. Fran Bagenal is not here yet, but it was claimed. She was claimed on her behalf that the Jovian magnetosphere is the biggest thing in the solar system. And then the caveat was, well, except for the solar system itself, but that's that's cheating. The solar system is not inside itself. So here's the magnetopause worked out. The magnetic field of Jupiter is big. Anyone remember? I said it, and Mark also mentioned some of the contributing factors to why we have such a strong magnetic field in Jupiter. Yeah, well, number one, the magnetic field comes with a dynamo. It's a really kick-ass dynamo. And it's a kick-ass dynamo because Jupiter has all this heat flux coming out of it. That's stirring it up like crazy. Okay, and it's rotating really fast. That doesn't hurt. Yeah, so it's got a strong magnetic field, sort of 10 times stronger. And the other thing that comes to its rescue, it's further away. So the density, the ram pressure has fallen off a bit by the time you get there. So we're talking 50 Jovian radii. That's pretty big. That the magnetopause itself is basically half the radius of the sun. And as we'll see, that's only part of the story, because that's the day side. That's when the solar wind hits the planet, and it goes around the planet, and it goes around the planet and basically creates this big tail downstream. Now, part of the story of this tail is we have to have magnetic field lines that when they get hit the Earth in the simple version where the magnetic field from the sun is going southward IMF, and that from the Earth is going northward, then there is some reconnection going on at the day side, and that's actually breaking magnetic field lines in the solar wind and connecting them to the Earth, and then they get to go around in this two-dimensional picture. Originally, I think due to Dungy, they go around to the backside, and then they have to reconnect on the backside and then come back into the night. So this is sort of the picture of the magnetotail, okay, and also a neutral sheet behind the Earth that is the Earth's magnetotail. This goes way, way far out, okay, and the size of it is really controlled by the rate at which this reconnection goes on. Do I have sort of 10 minutes? So one of the things is when you have this thing in balance, again, steady state. So the number of field lines being reconnected at the front, which is controlled by the solar wind, the phi dot flux rate of change of flux at the day side must be balanced by the rate of change of flux at the night side. And that requires a very long magnetotail. So what we get, sort of a more, and this really is much closer to a correct to-scale diagram. The field lines coming out of the South Pole are not going up to the North Pole. They're actually been dragged out by the solar wind, and they're just basically going away from the Earth. And the ones on the northern hemisphere are coming towards the Earth. And so we have, curl B, we have this neutral sheet, this current sheet, draped behind the Earth's behind the Earth. That is current crossing this way, separating outbound from inbound magnetic field lines. And the balance occurs, we have some amount of open flux, phi in the tail, okay? And that is the amount that's required in order to have enough reconnection going on here to balance what's going on at the front side. So we have phi dot at night equaling minus phi dot at the day, so those two balance. We have this long tail, and you can see that this is actually going on in other planets as well. Right? So we have this very long tail going on. And between them, we have to have this boundary between those field lines that are being reconnected and moved around and those field lines that are just basically always open. Okay? So this is the boundary between closed and open field lines in the magnetosphere, and that is the auroral oval. That is, this is from image, I believe, which is showing us in ultraviolet where that boundary between closed and open field lines is, going right over northern Quebec, I believe, and Alaska, down there. Okay, and nothing I've said has been, oh yeah. So let's just think about this. If this magnetotail has to be in flux balance, in reconnecting flux balance, it also has to be in pressure balance. The magnetic pressure, b squared over 8 pi, or b squared over 2 mu naught, must balance the plasma pressure, not the ram pressure, because it's basically going out, of the solar wind. And so you can basically say, there's b squared over 8 pi, and you basically have the certain amount of flux, which gives you the total amount of flux in the polar cap. And that is the radius, and it is sort of 25. Well, this is actually 25 Earth radii. So it's only 12 Earth, or yeah, when I worked out, 12 Earth radii from there to there. This is quite a bit bigger, 25 or so. And again, it's going to change with the pressure of the solar wind. There it is in Jupiter. There it is in Saturn. Again, same story. They have good dynamos. They're presenting this nice squishy obstacle to the solar wind. Solar winds dragging out their tails. But here's something that one might stay awake at night thinking about. The dynamo has all these magnetic field lines, and I argued it has a pretty good magnetic Reynolds number. So the magnetic field is frozen to the liquid core. So all those field lines are frozen to the liquid core. And yet in here, they all seem not to be moving. And up here, they are moving. They're moving very fast. It takes, a couple hours to get through here. And the turnover time in the core, 500 years. What's going on? I thought they were frozen. Well, the frozen in flux theorem, and we didn't really dwell on this, but if you've had plasma physics, that applies when the conductivity is high. The conductivity is high in the core. The conductivity is very high up here. But there's one layer where it's not high. That is our neutral atmosphere. So we have two high conducting regions, large, highly conducting regions, separated by kind of a layer where there's no conductivity. And so in these highly conducting, people will often say, well, that's because magnetic field lines are imaginary. And I have a tirade I usually go through, pointing out that a hockey stick is imaginary too, right? It's just made of air. Right? And I play hockey, and so I can tell you that when I've been hit by someone's stick, and the ref never seems to see this, but it does not feel like I'm being hit by empty space. Right? It hurts. And that is because what really matters is not what it's made out of, or whether it's real or not. It's whether it can communicate forces. And the defenseman will usually have a considerable amount of force on his end, and somehow that gets transmitted to me at the other end of the stick. Exact same thing in magnetic field lines. They transmit electromagnetic forces, basically Alfvén waves, along the field lines, and it hurts. It's every bit as real as a hockey stick is, as long as the magnetic field lines are moving that plasma with them and communicating forces. In a neutral region, that is not the case. Right? And so there the field lines are imaginary. So in this room, magnetic field lines, you can think of them as imaginary. If you're in space, you better not think of them as imaginary. They're real. Every bit as real as a hockey stick. All right. So what are we to make of all this? Well, I have the upper boundary where the solar wind is moving my field lines at some speed and moving them, in this case, let's say it's moving them to the right. And let's say the magnetic field lines, the magnetic field is going down, so I'm in the northern hemisphere. And if I turned this on all of a sudden, I would get a bend in the magnetic field, which would actually translate into current coming out of the page. And so I have J coming out of the page, B going downward. And so I have J cross B, which is a force that would be to the right. And this is actually the Alfvén wave. This is basically going to transmit that force down, and it's actually coupled to an electric field. The electric field here, V cross B, or minus V cross B, is out of the page. So we have an outward force electric field here, is not related to the current. Right? As we remember, electric field in the reference frame of the conductor is basically zero. The current is not. The current is there. But the current occurs down here. The electric field occurs up here. So you see the plot here. Here's the electric field. Here's the velocity. The current is this layer where the electric field is changing, but it's really there because the magnetic field is changing and the velocity is changing. But that moves downward. And you get to the ionosphere, and suddenly you no longer have these real field lines. But what you do is you still have this current, and it's flowing through the ionosphere. But the ionosphere is mostly neutral. So you have these charge carriers moving through it, but they're feeling a substantial reluctance to allow them to move. That's a resistivity. So at this place, you actually do have a match between current and electric field, and the current is actually sustaining an electric field in the ionosphere. Now, below that, you have just a neutral atmosphere. And it doesn't care at all about the electric field. It allows the electric field to exist there with no current. So what happens is that current basically ends up stuck in the ionosphere, and the electric field is the same everywhere. So you have the same electric field in the magnetosphere as you have in the ionosphere, and as you have neutrally. And what it actually ends up looking like is it looks as if the field lines, which are very real in the magnetosphere, as real as a hockey stick, are just sliding along the ionosphere. They just slide along because below the ionosphere, they're not real. So it's as if that's where they really come into existence. So these field line motions that are imposed by the magnetosphere and by the solar wind, they create a current in the ionosphere accompanied by an electric field in the ionosphere. Okay? And what really happens then if you follow in this is, sorry, I haven't been drawing your attention to this. This is the entire scene, but viewed from this side here. So what you're seeing is current, and if I had only a portion, a slab of this that was moving to the right, then I actually have only the electric field within this slab. I have velocity, actually you're viewing it from over here. So the velocity appears to be going away from you, but the velocity is only in a slab. And what you actually have then is the current that separates the slab that's moving from the one that hasn't. That current goes down, crosses through the ionosphere, and then goes back up. This is the current path. It's basically separating out that slab. Okay? And yeah, so that slab. And so what that means is when you have the MHD flow is imposing motion of the field lines very far away where field lines are real, it creates in the ionosphere this electric field, and you can integrate this electric field. This is the polar cap potential. The cross-polar cap potential, sorry. Not used to saying that. But it's basically just the integral of this electric field. This is phi dot. This is that same electric, because all the field lines that are reconnected at the day side have to do this. They're actually the ones that are moving across the polar cap. And so if I do this integral, that's what I measure. And this is how those field lines move. They move along here. Remember, this is sort of the real motion, but then the real motion is kind of translated into a fictitious motion at the top of the atmosphere or the ionosphere. And it sort of closes like that. So that's where you get this cross-polar field, polar cap potential, or I think these are figures due to Vasiliunius. Here's sort of that same map. This is what is known as the convective flow. And then finally, there was this story that where those slabs ended of moving, you actually get these currents. And this is the sort of current system that comes in. Here's a typical polar cap potential, 50 kilovolts or something. Okay, so that tells you that these field lines basically do their whole thing in about 5 hours. So that just brings us to 10 o'clock. Let me summarize then. We have this ionosphere. It's created by EUV and X-rays. Okay? It does diminish at night because the source goes away, but because it takes a while for those electrons to recombine, it persists for a while until the following day. So it diminishes this way. Then we have the solar wind, which, if we didn't have a magnetosphere, would be deflected by that ionosphere. That's what happens at Venus and Mars. However, if you have a magnetosphere, the solar wind is actually deflected by the magnetosphere, and that creates this interaction with the ionosphere through the motion of the magnetic field lines in the ionosphere. All right. Any questions then on this? Very superficial. You will hear people who really know about this stuff talk about this stuff in more detail, but this is sort of big picture, putting our whole heliophysics system together. And we have 2 labs, that's right. So you certainly will see a lot more of these things. All right. Now I think, Nick, are we sending up a couple people to talk about their posters before we break for 1 hour?
You'll have to go get water and go to the bathroom and
Okay,
come back.
we'll do the switch over. Sit down for a few minutes. Here's some advertisements,
Go get water,
our sponsors.
and we'll advertise the posters.
Then we'll take. Okay, so let's go to do a little bit of break, then we're going to get a really long break.